Hello, today we're going to be going over 4 topics that relate to pressure, temperature, and how they relate to water. First off, we're going to draw an illustrative diagram that relates water to its pressure and temperature, and we're going to draw a pressure-temperature curve that represents that data. After that, we're going to think of a couple systems that work with that graph or can be represented by that graph. Then we're going to talk about how we can get to the triple point of water and what kind of system that would have to be. And then after that, we're going to work on a problem that relates all of these concepts together. So first things first, I'm going to bring up my whiteboard here and let's get started. So first off, we want to look at a pressure temperature curve. Now, we've probably seen pressure temperature curves earlier on, and the general shape is going to look like this. So we have our y-axis, our x-axis, we have pressure here, we have temperature here, and we have kind of a look that's kind of like this, or some variant of this. Now, in this first region here, we're going to have our solid phase. So this is our solid phase. This is going to be a solid water, aka ice. So if we go over now into this area here, whoops, erase that. If we head over into this little area here, we're actually going to get into our liquid phase. This is going to be our liquid phase, and that happens when we increase temperature from the solid phase and the liquid phase. And so actually this line here, since we are going from a solid to liquid phase, this is called the fusion curve. Fusion curve. And that's this one right here. Right? So let me actually highlight that in this color. Here is our fusion curve. Now, last but not least, of course, the last phase of the water is going to be gas. It's going to be gaseous water, water vapor. And so we can see that we can either go from solid to gas here, or we can go from liquid to gas up here. Now, if you remember the term for going from let's use orange. If we remember the term from going to a solid phase to a gas phase, that is called sublimation. So this is just called the sublimation curve. Sublimation curve. And of course, going from a liquid to a gas, that is just going to be your vaporization curve. So highlight that. Here is our vaporization curve. All right. So now, apart from these 3 curves that we have here, there are a couple spots that we also want to take a look at. And these spots are going to be right here and right here. So, namely, this is going to be our critical point. Critical point and our triple point. Triple point. Right? Critical point and triple point. Now, at our critical point, this is when we heat up a liquid or heat up a gas enough at certain pressures to create what we call a supercritical complex. And depending on the temperature and pressure that you're in, you are either going to have a supercritical fluid or a supercritical gas. However, we're not going to focus too much on that for purposes of this video. What we are going to focus on, however, is going to be this point right here. And that is our triple point. And as the name would suggest, this is where our solid, liquid, and gaseous phases all converge. We see how the fusion curve, sublimation curve, vaporization curve, they all kind of meet at this little spot, which is called the triple point. And at this triple point, you can see all 3 phases occurring in one system. So we have solid water, which is ice, we have liquid water, which is water, and we have gaseous water, which is water vapor. So you will see all 3 of these phases in one system, when you're at this certain pressure, let me do something here. When you are at this certain pressure and this certain temperature, this is going to give you your triple point. And it only happens in this combination of pressures and temperatures. So that's going to give you a good visualization of what a pressure temperature diagram will look like in terms of water. So now that we've covered what this illustrative diagram is going to look like, now let's look into what the real life application for a graph like this is going to incur. So let me just move over to the side a little bit here. And I'm just going to draw, let's just say you have a glass of water, right? This is my glass. It's very fancy looking, but it's a glass, all right? And now let's say that we have water right here. This is our water, a glass of water. However, at room temperature, water is not the only thing that's in this glass. There is the atmosphere surrounding us. There is air surrounding us. And of course, this glass is no exception to that rule. We're going to have air, which is going to be this highlighter for now. We're going to have air in this cup. And so this graph does not apply to whatever is going on over here, because we have to think of a concept which is known as, this is a mouthful, so get ready, the pure component, saturation, vapor pressure. Vapor pressure, come on. The pure component, saturation, vapor pressure. And what that means is when we are working with a substance that is in a system like our cup here, we are working with something called the pure component. And the pure component speaks for itself. It is a pure component. It is a pure substance. It is not tampered with by any impurity. So let's say if you have a glass of tap water, there's all these minerals, there's all sorts of refining agents. It is not technically a pure water sample. So when we say something is a pure component, it is a pure substance. We need pure water. We need pure ethanol. We need pure alcohols. It is a pure substance that we are working with. And that is what this graph focuses on. This graph is a pressure temperature diagram for any water system that is pure and is at equilibrium. So when we take a look at this curve right here that separates our liquid and gaseous phases, of course, in the liquid phase, we are going to have water, and in our gaseous phase, we're going to have water vapor. However, this graph focuses on the equilibrium. Now, what equilibrium are we exactly talking about? Well, that's where this part comes in. This is where our saturation vapor pressure comes in. So, let's move over here. When we talk about water systems like this, we have a term known as the interface. The interface. And what that interface is, it is that thin layer of water that separates the atmosphere from the liquid water. That separates the vapor pressure from the liquid water. And so what we say about the interface is that equilibrium conditions always hold. Always hold. Hold. So at the interface, equilibrium conditions are always held. And so the pure component, so let's go PI VAP. The pure component vapor pressure of water, so H2O, is going to be equal to the partial pressure of H2O in air. So what are we saying? What do we mean by that? So let's take a snapshot over here. In the air, we have multiple elements. We have oxygen, we have nitrogen, we have carbon dioxide, we have vapor pressure in our air. And though maybe a very minuscule amount, there are particles of vapor pressure in that atmosphere. And so it is a partial pressure of the total pressure of air. Because we know by law of partial pressures, let's move over a tiny bit. Come on. We know that by this law, the total pressure is equal to the sum of the partial pressures our total pressure is equal to the sum of the partial pressures. One of these partial pressures is going to be the vapor in air, water vapor in air. So when we talk about the interface and what this equilibrium is and what the saturation is, we are talking about the fact that whatever the vapor pressure is by this water source at the interface, which is going to depend on the temperature, it is going to be equal to the partial pressure of water in air. That is the equilibrium we talk about. So it is only under these conditions, one being a pure component, and two being in equilibrium, can we achieve a system in which this curve is accurate and is applicable. So what we have to think about is, how do we get all of this air out and just replace it with pure water? Or how do we create an atmosphere, a system, in which it is only a pure component system? Well, we know one thing about water, and it is that it boils, and when it boils, it goes into water vapor. You stay there. So let's drop a system. So let's say I have another container of some sort. I still have water in it. Yeah. There's water in it. And originally, we are going to have air up top. So we're going to take advantage of the fact that water boils at 100 degrees Celsius. We are going to have some sort of heat source denoted by this orange here. Say that's like a stove top. You're boiling water for your coffee or your tea. It's the same process here. So what we're going to end up doing is we're going to boil all this water. And when that happens, we are going to replace whatever air is up here with this water vapor gas. All gas. Right? So now this container is full of water. We assume that no more air is left in this container. The water that we are using is as pure as you can get it. And what we're going to end up doing is, once it's brought to boiling and we let it boil for, maybe a few seconds, make sure all the air really gets out of the system, we're going to cap it off. It becomes now a closed system with only water vapor and water inside it. And essentially what we've done, we have now created a system in which the only component is pure water. So now, this graph is now applicable for this system, because now we have removed all the air. There is no more impurity in the water. We can now say that this system here is now a pure component. And now that fits both the criteria we have here, pure component, and it is in equilibrium. Thus, we can now use this graph to find triple points, critical points, all sorts of things. So now let's go back to this idea of a triple point, right? The triple point, remember what we said, it is where all three of these lines or segments converge at one point, which we call the triple point. And we call it the triple point because all three phases of water are present at this combination of pressure and temperature. Now look over here. We see that at the fusion curve, where it intersects at the triple point, we go from a solid to a liquid phase. So we can take a look at that and say, oh, well, the fusion point of water happens at around 0 degrees Celsius, which holds absolutely true for the temperature. As you can see, this is the triple point of water is actually at 0.01 degrees Celsius. So very, very close to 0 degrees Celsius. But in reality, that 0.01 makes a load of difference, and it is very hard to attain that temperature. However, if we look up on a table what the pressure is at 0.01 degrees Celsius, we get 611.66 pascals, PA. So now we have our critical point, our triple point, not critical point, our triple point temperature and our triple point temperature. Well, taking what we learned just before by having our pure component of water, how would we get to that triple point? Well, obviously, we'd have to go back to this situation here, this system, where we have 100% water in this system. So what would end up happening is we would need to get a container. We need to put water in it. We would need to boil it, wait a couple seconds, make sure that the boiling water pushes out all of that air, displaces it, and then it makes it all water vapor. Then we cap it off. So now we have this bottle of just pure component water. And what we have to end up doing after that is we need to, oh boy, not what I wanted to do. What we need to do with that substance is we need to bring it to 0.01 degrees Celsius and which would bring it up to 611.66 pascals. So this is where our triple point lies. This is how we can get a substance of water at its triple point. Now, mind you, we can't just use any old cup. If you put a cup in the freezer, put it at 0 degrees Celsius, it is going to freeze. Even if you bring it to 0.01 degrees Celsius, it won't go to the triple point because it is not a pure component of water, which is why we need to do this whole boiling process over here in order to create a system in which it is pure component water, and now we can use this chart and its pressures and temperatures in order to obtain a sample of water at its triple point. So now we're going to shift gears into a problem that takes all of these concepts into one and applies it into a real world scenario, as we kind of see here. Now, what's being drawn out here is this is a container that has a piston on top of it so that the piston pushes down on this system. We are going to keep the temperature constant at 80 degrees Celsius, and it just so happens that at 80 degrees Celsius, the partial vapor pressure of water in air is 47.4 kilopascals. So let's look at this. Now, we see that we have two phases of water in one system. We have our liquid H2O and we have our vapor H2O. When we push down on this system, we can look at a very famous equation that relates pressure, volume, and temperature, which is PV equals nRT, the ideal gas law. Since we are only at 47.4 kilopascals, the ideal gas law can apply to the system. So let's take a look here. PV equals nRT. We are keeping our temperature constant and we are decreasing our volume. So what's going to have to end up happening to keep this temperature constant? So let's make this into a thing. Let's go V equals nRT over P. Right? Our volume is equal to moles of gas times R, which is your gas law constant, times T, which we are keeping constant at 80 degrees Celsius, or I guess that's 353 Kelvin, over your pressure. So what's going to happen to this pressure as we keep decreasing our volume? Well, the answer is nothing, surprisingly, because we could take a look over here to this liquid phase. So we still have some vapor H2O here, liquid H2O here. However, can you see that the volume of the vapor here and the vapor here these are not the same. The volume has decreased. So you must be asking now, what changed? Well, it wasn't the temperature. We're keeping that constant. And so the other question is, did the pressure increase? That's also a no, because we have liquid water in our system. What we essentially have is we have an equilibrium between H2O liquid and H2O gas, right? We have our liquid phase here, we have our gaseous phase here, and remember at the interface, the pure component saturation vapor pressure is equal to the partial vapor pressure of water in air. So these two are in equilibrium. And what do we know about decreasing the volume of gas in a system? Well, if we look back to our old friend Le Chatelier, we're going to shift back to the side with less moles of gas. That's the law here. So what actually ends up happening is our vapor H2O condenses. It releases heat and it goes back to the liquid form. And so we are letting off heat here. Let's illustrate that. Heat is being let off, yeah? But hold on, I thought that the temperature of the system is supposed to be constant. I hear ya. So actually, in order to keep a constant temperature here, we have to cool the system down, right? Because we are releasing heat, and so the system is going to be warmer. So what we actually have to do is we have to maybe put it in an ice bath, or we can put it in the fridge while this is happening. In order to keep this temperature constant, we are going to need to cool down this system. And so we can see that our volume constantly decreases. Let's go one more iteration of this. Go over to the side, draw out a new container. Here. Here's a container. And let's say our piston has now reached all the way over here. And all that's left is liquid H2O. At this point, all the vapor H2O has now been compressed. It has now condensed into the liquid form. So what we have here is liquid H2O. Right? At this point, what we have essentially done is we have reduced the total sample volume of the system. Because think of it. When we go over here, oh, come on. What's going on here? I don't want you. When we go over here, we see that we have this volume over here. All of this vapor is spread out. Vapors have much more capacity to move around and be random, so it takes up a lot more volume than just liquid water. So we see that we keep decreasing our volume stage, and overall we are just ending up with a lower volume than we started with, because all of that random vapor, all this spread out volume has now just condensed into liquid H2O. So the answer to the question is, if we keep pressing down on here until nothing but water is left, we are condensing the vapor phase into the liquid phase, and we would have to be cooling the system in order to keep a constant temperature. This was all for today's video. I hope you learned something, and I hope you have a nice day.